video. I'm currently at Wilson's Commons, so you might hear a little bit of background noise, but here we go. So today we're going to be doing area with polar coordinates. So basically integration for area, but with polar coordinates. So the way that integration with polar coordinates work is that if you had a function, right? If you had a function here, r equals f0, or sorry, r equals f theta, and it exists from angle theta equals alpha. So it exists from this point here and all the way until angle equals beta, all the way until here, right? Until this point here. If you were to integrate a specific portion of this area. So first of all, the integral of the whole function r theta over the whole kind of over this whole kind of section here, the area you get would be this, in this kind of like cone shape. You wouldn't get, what I was thinking at the start was you might get something like this, where it's like down on the area underneath, right? But no, it's not. So when you do with polar coordinates, the thing is you do it with, what happens is you make basically, a cone and you get the area in that cone, which is really interesting. So when we integrate for area with polar coordinates, it's no different than integrating with the other things. We want to think about finding the area of a slice and then worrying about kind of adding that together with the limits and everything. So let's look at an example, right? So for example, with a circle, you'd had an angle theta, and you had radius r, and if I asked you to find this area here, this would simply be kind of like this. If we're looking at this, and if we want to find the area of this slice here, that would be as simple as saying 2 pi over 2 pi, sorry, theta over 2 pi times r squared, right? Because technically what we're doing is we're doing pi over 2 pi times pi r squared. Sorry, this is the right equation. So what we're doing is we're taking the fraction of the theta over the full circle and multiplying by the full area, right? So we're thinking if theta is equal to 2 pi, if theta is equal to 2 pi, then the area would be pi r squared. So if we use kind of an equation, right, 2 pi 2, or I put down here 2 pi 2 pi r squared, this is pi r squared, then if we divide it by 2 pi on both sides, well, you guys, 1 goes to pi r squared over 2 pi, you cancel these out. Therefore, theta is going to be equal to r squared over 2 times by theta because we took 1, we multiplied by theta here, so we have to multiply by theta on this side. So theta is equal to r squared over 2 times by theta. And so what we have here is the equation of the angle dependent on the angle here for any circle. And the idea is that this is no different from a circle, right? We can treat this as a circle. That's just how the equation works. And so this is no different from a circle. And so we can use this and we can just integrate this because this is a small section, right? We can treat this as a small section and then we're going to integrate this. So let's kind of think how we're going to do this. So area of a slice is equal to this. Therefore, we're trying to integrate. It's going to be alpha beta of 1 over 2 r squared d theta. Okay, so let's do a few examples with this. So we have a circle. This is going to be really simple, right? So insert page above. We know the equation. It's going to be from alpha to beta, 1/2 r squared d theta. Just going to do a few examples with you. We have a circle here with the equation r is equal to r0, which just means it's a constant. We can say it's r equals a, for example. So r equals a, this length is going to be a. Remember, this is polar coordinates. Remember, give me a second. Remember that the equation is technically in the form r equals f theta, right? But if it's a here, there's 0 thetas. Imagine just like 2, right? R equals 2, for example. But we're going to say it's a. Okay. So simple as this is going, what we're going to do is with integration, it's always kind of one directional, right? You want to be working from top to the bottom. If you took this area and then you also took this area, they would actually cancel out because they're kind of negative and positive. So what you want to do is you want to do from this end and then integrate all the way to this end. So that's going to be an angle of pi or 180 degrees. And what we're going to do is we're going to be integrating from 0 to pi because that's the path that we're going, right? The path that we're going is we're going from 0, right? This here, right here is 0. That's 0 from the x's. And then we're going this, pi over 4, pi over 2, 3 pi over 2, pi. So we're going from 0 to pi. And we're going to do this, the simple equation. And remember, this is only 1/2, so we're going to multiply 2 into this. X2 because just half. Okay, 1/2 r squared. R squared in this case is the function, so it's just a squared d theta. What we can do now is we can take everything out. The 1/2 and 2 cancels. We just have a squared multiplied by the integration of 1, which is just going to be theta, pi, and 0. And what we end up with is pi a squared. Or equivalent here is pi r squared, right? But the r in this case is a, so that's why it's a squared. Okay, so let's do another example where we have this. So we need to find the so this is the graph that we have, and we need to find the area enclosed by one petal of the rose. So this is r equals sine 2 theta, and we want to find the area of one petal. How do we do that? Well, let's find the kind of limits of one petal first. We're going from 0, and we want to go, one petal ends about here, so we want to go all this angle. This is going to be pi over 4 or 4 degrees, and we can check this, right? It goes from 0, so it starts at 0. Sine of 2 times 0 is going to be 0, so it starts here, then it goes out because it's increasing angle. Then as we get to sine of pi over 2, we put pi over 2 into here. Well, 2 times pi over 2 is going to be pi, and sine of pi is 0. So the equation goes back to 0. So this is exactly one petal. It's going to be from 0 to pi over 2. And we're going to be integrating 1/2 and the equation squared. So it's r squared d theta, and r squared in this case is sine 2 theta. And I'm not going to go through with the integration steps for you because this is not an integrating video. It's a getting area of polar coordinates video. So it's more theoretical. So if you want to see kind of how I did it here, I'll just show you how so you use the double angle identity, and then you can go all the way down, and it ends up with pi over 8. Okay. So now we need to look at the area between two curves in terms of polar coordinates. And it's really simple. You just take the area of the big one minus the area of the small one, which is the same way we've been doing as with everything. So you just take this and you minus this. And I don't know if you guys can see how this equation is derived, but it's basically saying alpha beta of, remember, it's 1/2. I missed a 1/2 here. Wait, no, there is no 1/2. Is there? Give me a second. Okay, yes, there is in fact 1/2. I copied this wrong. So yeah, this is going to be 1/2 of the top one, which is g theta. So g theta and that squared, right? Minus the integral from a to b alpha of beta of 1/2 f of theta. That's the bottom one squared. And then what you end up with is just simple as this. You group them together. So when I first saw this, I was just a bit confused because I couldn't think of like the algebra with the integral, but this is how it works. This is completely right. Okay. So now you guys can see that. So let's try doing an example here where copy this. And again, this is just gonna be, I'm not gonna do the full calculations. I'll show you my full calculations later, but this is all I want to show right now. Okay, so we want to find the area. We want to compute the area outside the curve r equals 2. This is r equals 2 right here, the circle of radius 2. And inside the curve are 3 plus 2 cos theta. Okay, so that's the curve right there. And I think when you do this question, actually, we're going to do this right now. We're going to do this question, and we're going to go through the steps. Okay, so I already gave you guys the spoiler to the shape, but basically, let's think about it. So if r is equal constant, it has to start off, so when theta equals 0, it's a 2 distance. When theta equals pi over 4, it's a 2 distance. When theta equals pi over 2, it's 2 distance. So it stays constant like this. It goes at 2 each time. Okay, and now we have 3 plus 2 cos theta. So 3 plus 2 cos theta, let's start from 0. Cos of 0 is 1, so it's 3 plus 2. Starts at 5, right? And as we increase cos theta, if you remember circle, right? As we go towards the center, cos theta is going to be equal to 0 because the x-axis is actually just cos x. So as we go to the 0, as we go towards pi over 2, or 3 pi over 2, we end up with cos equals 0. So then cos equals 0, but then plus 3, so that's still going to be 3. So it's going to end up like looking at here where this is 2 and this is 3. Okay, and now when we get to cos equals pi, right? Once we get to here, cos pi is equal to minus 1. So 3 plus 2 times minus 1 is 3 minus 2 is going to be 3 plus 3 minus 2. Let me just check. Okay. I could have sworn, I think I wrote this equation wrong or something, but somewhere, I don't know, maybe I copied it wrong, but actually cos of pi is -1, so 3 minus 2 is just 1. So technically, shouldn't it look like this? I'm not sure. I'm gonna draw the way the question looked. And I swore the calculations worked out. But yeah, this is how it looked. So this, sorry guys. So this here crosses at -1. And this is kind of the shape of the equation. And both sides are going to be symmetrical, right? So if we want to find the area outside the curve r equals 2, so the area outside here, right, outside the curve, so outside of the circle, but then within the curve r, so it's going to be this area sandwiched in between. Can you guys see that? And this is symmetrical. So if we find the top half, we just need a times 2, and then we can find the bottom half. Okay, and the biggest thing with this is what you want to do is to find the intersection point. Because if you were to find, for example, because 3 plus 2 cos theta, and this is just 2. So this is r equals this, r equals this. So because we see that r equals 3 plus 2 cos theta is on the outside, we want to take r equals 3 plus 2 cos theta minus r equals 2, right? But then here, we can see that actually r equals 2 is larger than r equals 3 plus 2 cos theta. So if we were to do all from 0 to pi in this, we would be calculating this negative area where we're taking the circle minus the pear shape, and we'll be adding that to the positive area here. So we have to find the angle through which they intersect and only integrate to that angle, and that angle would be here in theta. So let's figure that angle. So we need to equate these two graphs to find the intersection angle. So 3 plus 2 cos theta is equal to 2. Because r equals 2, r equals 3 plus cos theta, so I just put r1 equals r2, and that gives me, so this is 2 cos theta is equal to -1. Therefore, cos theta is equal to -1/2. Yeah, and so if we draw the cos graph like this, we see that -1/2 is going to end up somewhere like here. So this is pi over 2, and to go from 0 to 1/2 on a curve, this is 30 degrees. So that's pi over 6. And what we have is pi over 2 plus pi over 6, which is going to be 3 times this. So 3 here, so this is going to be 4 pi over 6, or equal to 2 pi over 3. So now we know that this angle here is 2 pi over 3. And all we have to do now is set up the integral. So from 0, because we're starting from this line, we're going from 0 to 2 pi over 3, and we take 1/2 of g of the one on the outside. So we have, so 3 plus 2 cos theta squared minus the graph of the inside, which is just 2 squared, and all this d theta, and that's the equation. And you can do the integration from here. So yeah, and I think from here, we were just doing the opposite. So we found this area right here. And basically, this is the same idea. It's just that now the circle is on the outside and the pear is on the inside. So we just have to reverse it. And you have to do this kind of limit here. So we're going from, can you imagine what the limit is? So we're going, if we had, so the first one we're doing is this one, which is theta. And then we're doing them to this one. So that's until pi, right? So what we're going to be doing is we found what theta was 3 pi over 2 pi over 3 all the way to pi, and then that's it. And then you just do the whole thing again, but with the circle on the outside this time. So it's 2 squared, so 1/2 of this, and then we have 2 squared minus the inside equation, which in this case would be r equals 3 plus 2 cos theta, 3 plus 2 cos theta, and all of this squared, just like before. See, that's it, guys. That's the kind of idea. The most difficult part is just to do the limits like this and finding where they kind of like, which is the appropriate limits. Oh, and make sure you have to times 2 to this too. So technically it would just be like a normal one because we're only finding 1/2. If we found, technically, if we did this whole thing, which would be from 3 pi over 2 to, in this case, minus 3 pi over 2, or you can say also 3 pi over 2 plus whatever it is. If you found the limits here, you'd actually equate the angle area to be equal to, actually, I'm not sure. I believe it might be 0 just because we have a positive area and a negative area. I am not sure. But generally, I think doing the half is better, and being aware of that is also better. So thank you guys so much for watching. You guys, see you guys never.